Hello everyone, welcome back to Electronics 1. So the last couple classes we were looking at the PN junction under the case of zero external bias, and I just want to, before we get into the case of forward bias, I just want to jump back there for a second. So we ended the last lecture by coming up with an expression for the built-in junction potential that showed that that potential is a function of our doping concentrations and our thermal voltage. But what I wanted to focus on a little bit in this class is, or just initially here in this class, is you'll note in the textbook that the width of the depletion region is not uniform in the N and P type material, and this is quite typical, and we're going to talk a little bit about this when we get into bipolar junction transistors. But just to briefly note that the reason for the larger width as depicted in this diagram of Cedra-Smith in the N region is because we're assuming that the N region is more lightly doped, so there's less majority carriers. So when that recombination occurs and that, well, when we say that charge is uncovered in the depletion region, so due to that recombination that occurs, the recombination has to go deeper into the more lightly doped material to uncover the same amount of charge to counteract the charge that's uncovered in the more heavily doped region. Okay, so we see the doping concentrations on figure B of this diagram, and you'll see that the doping in the P region is higher, as depicted by the concentration of acceptor atoms versus the concentration of donor atoms in the N-type material. Okay, so that's what leads to that the portion of the depletion region being wider in that N-type material in this example. And we see that kind of our 0 point is not directly in the center as I've been depicting it. That 0 point occurs is offset, I guess. And here's a diagram that shows that again, this is all based on the getting the same magnitude of charge uncovered, and this graph is just showing that how the charge densities, or the amount of charge that's uncovered, is a function of the charge density. So when we have a lower charge density due to a lower doping, we have to go deeper into the material to uncover the same charge, and the area of the blue area here and the gray area are being depicted as being equal, but again having to go deeper into the material to get those matching areas. Okay, so with that, let's jump back to today's lecture, where we want to talk about the forward biased case. Okay, so what happens to this PN junction when we're under forward bias? Okay, so I just draw a diagram of my PN junction here again, and this being my P material, this being my N material, my P having been doped with acceptor atoms, my N material being doped with donor atoms, and we know that there is a depletion region here in the center. I'm going to show this um, to be equal with the depletion regions, just for simplicity here, but now we know that they don't have to be equal, and we just had a quick look at why that is the case, and to understand why the textbook might show them that way. Okay, so this is representing our diode, and we discovered that we have some built-in junction potential. So this is our built-in junction potential that we did some derivations for in the last couple lectures. Okay, but now what's new is we're going to take and connect a source in this matter, and we're going to call this VF to represent a forward bias. And again, as you can appreciate looking at the diode symbol, this would be a forward bias condition. Okay, so when we apply a forward bias, the forward bias VF here is going to effectively subtract directly across the built-in junction potential. Okay, and you might say, well, it's not applied directly across that junction potential, but the doping of these regions here is makes those regions sufficiently low impedance that this junction, this forward bias, we can treat it like it's applied right across the depletion region of the diode, and henceforth directly is going to subtract from that built-in junction potential. The result is that we get a drop in our junction potential, and that results in the additional minority carrier injection. So we're calling this the effective junction potential, that the drop in effective junction potential, and the effective junction potential is that difference between our built-in junction potential and our forward bias that's being applied, and this is going to allow additional minority carrier injection. Okay, so whereas in our unbiased case or zero bias case, we had a equilibrium established, right? The diffusion current and the drift currents were equal, as depicted in this diagram. Now, with the introduction of our forward bias, we are going to have a surplus of diffusion current due to this said effective drop in junction potential, right? So the net effect here is that we are going to get a net current flowing. Well, maybe I'll show it this way. We're going to get a net current flowing in this direction, which again, what we have already encountered is the case for a forward bias diode. We have current flowing through it in the forward direction, but that is due to the fact that now our that drop in junction potential allows the diffusion current to be greater than that drift current and result in a net forward flow of current. Okay, and it can be shown here that this results in so from the case of the zero bias, now we have a case where the minority carrier concentration in our P and N regions is disturbed. And if we have a look at figure 3.12 from Cedric Smith, just paste in this here, we see that, and again, just note that we're assuming that the N region is more lightly doped, and therefore we have a larger width in the N region of the depletion region as opposed to the P region. So just note that. And we see this, so the unbiased or zero bias concentration of minority carriers is shown with this dashed line on the bottom. Okay, so that zero here is referring to the zero bias concentration, right, in both of these cases. But now we can show the concentration of minority carriers right at the edge of this depletion region, as for the N type material, the concentration at the edge of the depletion region, so at XP, can be shown as being the concentration at zero bias times e to the VF over VT. And similarly, we can show that this concentration level up here in the P material is concentration of N at XN, so at this location, is equal to the concentration of concentration at zero bias times e to the VF over VT. We'll also note from this diagram that this decay in the excess concentration due to this forward bias as we move into the material. So these electrons, these holes that are appearing in the N-type material are due to now a injection of minority carriers due to the effective reduction in the junction voltage, and that increased diffusion current. But those holes, so these holes as they're injected across from the P region, they eventually, as they move away from the junction, they eventually recombine. So this decaying exponential, so this is due to recombination. Okay, and as those excess minority carriers, whether they're holes on this side or electrons on this side, as they recombine, we have a loss of majority carriers. Okay, so these electrons, for example, that are here, so these electrons that are recombining with a hole result in a loss of a hole here, right? So this hole gets lost in this P region, and that loss of majority carriers is made up from an external current, the forward current that flows into the diode. Okay, so let's see if we can show that graphically here. Right, so if we have a PN junction, I have my depletion region, this being my P material, this being my N material. I assume I have some forward bias applied to this, and let's just look at this from the perspective of a hole for a second. So due to that effective reduction in junction potential, I'm going to get these excess minority carriers being injected. Okay, so this here is when it arrives on the other side where it's a minority carrier. This is referred to as minority carrier injection, and that minority carrier might eventually recombine with an electron. So if this recombination occurs, well, I've now lost a electron in the N-type material, in which would suggest that it now has become more positively charged. So to counteract that, my external circuit here will have a neutralizing electron supplied. Okay, and this explains why we have current flow. And the same argument could be made from the other perspective, as we also will have electrons that will make their way across due to diffusion. They may find a positive or a majority carrier to combine with, and that recombination will result in a loss of positive charge in the P-type material, and that will need to get replaced from the external circuit. So we'll get a hole injected. So this hole from external circuit will be required as well. And even this hole that made its way across due to diffusion, maybe I'll show a different color here, This will also have to come from the external circuit as well. So we have holes being supplied there, and we have electrons being supplied here due to this increase in diffusion current. Okay, so here under forward bias, the balance that existed previously under zero bias between the diffusion and drift currents no longer exists. And the diffusion current far outweighs that of the drift current, and it also increases dramatically with increased forward bias, due to the nature of the exponential relationship and the exponential rise in minority carriers around the junction, as we saw up here as expressed in these expressions for the concentration of minority carriers at the edge of the depletion region. Okay, so that's hopefully gives a little better understanding of what why current flows and why the change from the zero bias case when we put a PN junction under forward bias. Next class we will go through a bit of a derivation to see if we can solve for the magnitude of that forward diode current, whereas today we've just kind of looked at it kind of qualitatively at this point. So we'll try to quantify it in the next lecture.